Hi everybody. This week's lab is to look a little more closely at algorithm analysis and Big O. And so what we're going to do is we're going to time some different segments of code and graph how long it takes to run this code given increasing amounts of input. And for the most part, that means bigger and bigger arrays. To help you get started, I wrote the code that will do the timing for you. So this video is going to walk through and explain how that code works, and will also show you how to use gnuplot to plot the graphs. Now you don't have to use gnuplot. If you have another tool you like, that's okay as well, but I wanted to make sure you had at least one tool that you had instructions on how to use. So you will find in the starter code a program called bigo.java, and like I said, what it does is it times segments of code and generates text files that you can then graph. The first thing we need to time code is we need some increasing amount of input. This helper function here, as you can see, just creates an array with how many ever elements we want in it, and then goes through and fills that array with some random integers. So it gives us some random data of whatever size we need. Here's where the different pieces of code that we're going to time come in. And so you can see some of the different things we're going to look at. Here we have a function that just finds the maximum value in the array. This adds up all the integers in an array, and this will multiply all the integers in an array so we can see whether addition is really faster than multiplication and how much. You'll notice right here, I have this little if statement, because when you multiply a bunch of numbers together randomly, it's possible that one of them will end up as 0. And of course, once you multiply something by 0, the rest of the algorithm isn't very interesting. So this keeps us away from that particular problem. And then here also, we're going to add up an array full of integers, but this time, instead of letting the integers just overflow, we're going to do the addition with what's called a big integer. And that is a class that can handle integers of arbitrary size. Here I went through an array and we're just multiplying all the pairs together. Imagine like you're going through a room and everybody has to shake hands with each other. Well, we're going through an array and all the numbers need to get multiplied against each other. This does it in a bit of a naive way. We have a complete nested loop here. This one does it in a smarter way so that we're not duplicating anything. This algorithm here just repeatedly adds numbers to the head of an array list actually, and this one repeatedly adds numbers to the tail of the array. Now the interesting part of the code here is to actually measure how long it takes. And so quick intro to some of the parameters here. This is the name of the file that will be created. So when we run the test, we'll put the data in a text file. That's the name of the text file. These are the parameters of the loop. We want to time code with different size inputs. So we might want an array of 100, an array of 200, an array of 300, and so on. So this is our smallest array as the start, the biggest array is the stop, and this is how big the step is. So maybe when we want to go by hundreds or 200s or 250s or something like that, just so that it doesn't take all day to run. And each time we do a measurement, of course, anytime you do measurements in the scientific world, you want to take multiple measurements because there's noise in any system. A computer is no different. So this is just how many measurements we take, and then you can take the minimum, maximum, average, or whatever. You can apply some statistics to that. Now, the part that's probably a little less familiar to you is when we go to measure the running time, we need to specify two things. We need to specify what code we're going to test, right? We somehow need to tell this method which of these methods up here we're timing. And then we also need to specify where the input's coming from. So this is using, both of these are Java functional interfaces, the same thing you would use for like event handlers in the GUI. All right, so let's see what happens here. The first thing we need to do is open the file. That's what's happening here. Because it takes a while to generate and run all the tests, I occasionally send some data to the screen just so you know that the program isn't hung. And so here's the loop These are all the different tests we're going to run. We're going to start with an array of whatever size, stop with whatever size, and that's how big. Are we stepping up by 100s, 500s, or whatever. Some statistical data here we'll collect. And like I said, we're going, for each test, we're going to run that test multiple times, just in case there's some noise. And so to make that work, so here the input factory is that functional object. It's that wrapper for the code that's going to generate our input. So when we call the apply function here, it's going to generate effectively an array of size n. This function here will just, as we'll see in a minute, points back to this helper. And then, so after we have our input, we will take a picture of what time it is. So system.nanotime will tell us what time it is in terms of like nanoseconds from some point in the past. This is our other functional interface. This is what's going to wrap up one of those algorithms we just looked at above. That's the code we're going to test. And when that code is done running, we'll go back to the clock and see what the stopping time is. And that will tell us how many nanoseconds it took to run the code. And then here we'll add up all of those times so we can do an average. We'll also keep track of the maximum and minimum. And when we have that, we will print all that data out to the file. And like I mentioned earlier, every so often we'll throw a dot up on the screen just so you know that the program hasn't hung. So now we want to test these different pieces of code we just call measure running time. This is the file we'll put it out in. Here's our start, stop, and step. So we'll start with an array of 1,000. We'll go up to 500,000. And in this case, we'll just take data every 10,000. So we'll do 1,000, 11,000, 21,000, 31,000, and so on. We'll do 100 trials. And here's how we specify what code we want to run. So when we say big O :random int array, we're telling it that's the method we want to run in order to generate the input. And this is the code we want to time. And so I've already got most of the different pieces of code that you're going to time set up here just to save you a little bit of time during the lab. And then down here, when you want to do a particular test, just uncomment whatever lines you want to run. I suppose you could uncomment them all. It will generate all of the output files, but it'll take a little bit of time to run. I think it's a little bit easier to work on them one at a time. So for example, the first step is to compare those three linear functions at the top, finding the max, and then adding up all your integers, and then multiplying all your integers. So you'll just uncomment the first 3 lines, run the code, and then you can see down here it's timing the find max function. The dots there show us that it's not hung, and we can see how long it's taking or how much we have left. And this is what the start, stop, and step is for. You got to find that balance between collecting enough data to be meaningful and not having to sit there and stare at the machine all day. You might notice that as you get closer to the end, the dots come slower and slower and slower. So think about why that is. Okay, and then when it's done running, what you'll see is it generated the 3 files it said it would. Here it was max.bigo, sumint.bigo, and multint.bigo. These other files were here before as I was testing out my code. So let's look at max.bigo. And what you can see is it's just a text file with numbers. This is the size of the array, 1,000, 11,000, 21,000, 31,000, and so on. And then you have the minimum, the maximum, and the average. You'll notice that the maximum, you occasionally get some really big outliers in here, because remember, many programs run on a typical computer at once. It's not just this Java program, especially if you're listening to music or you got your email open or something like that. So occasionally you'll get some really big outliers pop up in there. So I think for this lab, it's reasonable to look at the minimum. The minimum is the fastest it can be done if no interruptions or anything like that come in. Anyway, so this is just, like I said, a text file with those 4 columns. You can take and cut and paste those columns into whatever program you're comfortable using, whether it's Google Sheets or Excel or some other tool if you have it. But the one that I learned how to use and is right here at the command line for me and also on EOS if you need it is called gnuplot. So you just type gnuplot and it's a terminal program. So if you want to plot a function, I can say something like plot x squared, and it will pop up a window with a plot of x squared in it, ooh and ah. And if you want to plot the data out of the file, you put the file name in quotes. So if I say quote max.big O, then what it will do is it will plot the first 2 columns of that file we just looked at. And so that shows us the minimum, and as you can imagine, that should look more or less like a line. If you want to see more of a line, you can add with lines points. And that's just a preference of how you want to see it, whether you want it connected with a line or not. Now, if you want to plot more than one thing at a time, so if we want to, for example, compare adding numbers to multiplying numbers, then we just separate the file names with a comma. And we can see the multiply and the addition, and of course the addition is faster than the multiplication, one of the things you'll be looking at in the lab. And you can combine the two. Like if we want to take a guess as to what this coefficient is here, we can see that this is 500,000, this is 800,000. So that's about 1.3. So I could even add a mathematical function in addition to those data files. And then we can see the line on there. Okay, so my math was a little bit off, but you can play around a bit and try to find a line that fits well. So that's the basics of gnuplot. There's lots of cool stuff it can do, but it will get the job done here if you don't have a tool you like better. To include it in the lab report, you can either just do a screenshot or you can get gnuplot to create JPEGs or PNGs for you right from here. So I can do set term PNG. So I want to create a PNG file. I can do set output. I'll call it summult.png. It helps if I spell output correctly. And then I run the plot command again. And now when I exit, you'll see I have a file called summultiply.png, which I can open. And there you have it. I have a separate file with that graph in it that I can include in the lab report or do whatever I want with. So that should help you get started. I figured it was easier to explain that in words than to try to type that all out. I'm optimistic this lab will go reasonably quickly, but certainly if you have any problems at all, don't hesitate to let me know. Have fun with it. It's not required, but you might enjoy putting some of your own code in and trying some different functions, trying some different things to see what the different graphs look like. Have fun.